Today we are finally going to put all the linear algebra we have learned into actual code. Now that we understand the geometric structure of vector spaces in the last few videos, so it's time to put the theory into practice once again. So in this chapter, we'll take the hands-on look at the norms, inner products and NumPy arrays operation in a real life. Most importantly, we'll also meet matrices for the first time. Today we are going to implement every one of those concepts using NumPy. By the end of this notebook, you'll understand not only what these mathematical ideas mean, but exactly how machine learning libraries compute them. We only need one library, NumPy. So NumPy is the foundation of scientific computing in Python. So nearly every ML library like TensorFlow, PyTorch, Scikit-learn, JAX builds on the same idea, efficient multidimensional arrays. So, throughout this notebook, NumPy will become our playground for linear algebra. Before using NumPy, let's talk about why we need NumPy in the first place. So, why Python loops are slow in the naive approach as we are seeing in this code. This function adds two vectors element by element inside the loop one after another. This works internally, but Python executes each iteration individually. That means thousands or millions of tiny instructions are working behind that loop. Now you might be thinking, what is np and 0 np dot zeros and shape is equal to length is equal to x means? These all are related to NumPy library. We imported NumPy library as NP. Then NumPy provides us various types of built-in functions. So np.zeros give us a NumPy array filled with zeros, and np.array converts the list into NumPy array. So it stores the array in the variable x and y, and with the help of function add, we basically gets the additional vector which is based on naive way. Now compare with it with NumPy way. Here we go, x plus y, and we'll get the same number of elements and same value of arrays that we have get from the naive way. For confirming the answer of both, we simply use the np.equal function that will confirm the both approaches are agree. Here we can see in the code. There is no explicit loop, just x plus y. Yet NumPy still performs every addition. So the difference is that NumPy performs the work inside optimized C code rather than Python. That's called vectorization. Vectorization is basically performing an operation on an entire array or vector at once instead of using loops to process the one element at a time. So it is the one of the biggest advantages of NumPy because the operations are implemented in optimized C code and making them much faster than Python loops. Let's take another example. We took or imported the math library, which is built-in function available in Python. After running the below code, we'll get the type error that it says zero dimensional arrays can be converted to Python scalars. So basically, this built-in function expects only one number, or we are giving it an array. So it doesn't know how to apply itself to every element present in the array. So if we use NumPy or its module name np.exponential, then we'll get proper answer. Why? Because np.exponential is the universal function, and universal function automatically applies the operation to every element. Internally, NumPy does calculate the exponential of each and every element. But the real question is, why should we care? So it is basically based upon performance. So after running this code, if we look at the performance of both methods, we'll see performance of NumPy is much better than normal naive way. So if Python version takes 1 minute, then NumPy would finish the same work roughly in 1 second. Now it's time to go into the real interesting part, which is norms and distances and dot product. So let's talk with most important one, the Euclidean norm. A straightforward implementation would be the following one. And below that we have also added the NumPy built-in function, and we'll get the same answer as both. And as we discussed in last videos, norms have also the p-norm family, that will gives us, if p is equal to 1, then this is called Manhattan norm. P is equal to 2, which is known as Euclidean norm. And then until infinite, it becomes infinite p norm. And in this below code, we have calculated in both ways, as well as normal function and as well as in our built-in function of using NumPy. And then we have distance, which is just a norm of a gap. There is no any big deal here. And below that, we have finally have dot product. The dot product is calculated by multiplying corresponding elements of two vectors and then adding the results together. This only makes sense when both vectors have the same number of elements. For example, if X has 4 elements and Y has 4 elements, the dot product is valid. However, if Y has only one element like 2.0, and the dot product is not mathematically defined and should produce an error. If you compute it using np.sum function, then numpy broadcast y bat is equal to 2.0 into this vector. It multiplies it with every element of x and it returns a number instead of warning you. This can hide bugs because the result looks valid even though the calculation is wrong. That's why whenever you want the dot product, always use dot function instead of np.sum x multiplied by y. So np dot function checks that the vector size match and raises an error if they don't, helping you catch mistakes early instead of silently producing an incorrect results. Let's implement one algorithm, which is this one. This is a method in the linear algebra that takes a set of linearly independent vectors and converts them into a single orthogonal, which is or orthonormal vectors that span the same vector space. So why do we need this algorithm? So we use it to create an orthogonal basis or orthonormal basis because perpendicular vectors make many mathematical and machine learning computations much easier. So we have a given a set of linear independent vectors and we want to construct an orthogonal set. So first one, which is a projectional formula. So first one, which is a projection formula, the projection of a vector v onto a vector u is what we have calculated here. And here we calculate the projection. See the visualization carefully. And this is the final function which calculates our output. Here we are testing this algorithm which we have implemented. And here we got our final result. Now finally we are going to meet our the matrix. So this is ML's most important object. So matrix is a table of numbers, n rows by n columns, and it supports three core operations: scalar multiply, addition, which is element wise, which is same shape required, and multiplication, which is a row or row dot column dot products. So here we have one example and we have one matrix which is named as A and second one is as a B, and when we applied some operations like addition, multiplication, and applied exponential function on A, and here we get the results. We can also have the transpose of A. Here we again use the Python built-in one, which is a dot t, to find the transpose of A, and also we have used the NumPy's built-in function, which is transpose of A. If we compare the outputs of both results, then we'll get as a true, which is both transpose are equal. One of the most important part in matrices are that in matrix order is matters the most. Unlike ordinary numbers, matrix multiplication does not commute. Like a into b is not the same as b into a. Let's look at the example that a is equal to we have some vector and b is equal to we have another vector, and then we have multiplied them and we'll get the different results here. So this single fact is exactly why the order you stack layers in neural network matters. So you can't just shuffle layers around and expect the same model. Now let's see how NumPy actually stores a matrix. Here is the example. Let's ignore this part here, which is a class of matrix. Let's see how it works in the background. So if we use the metric class, which is we have initialized here, we initialize shape as 3 comma 4, which gives us 3 rows and 4 columns, and we have initialized values in, and here we have initialized one value in our matrix. After running this code, we'll get 3 comma 4 matrix, and which we have initialized one value here is 3.14. So underneath it is a flat list of 12 numbers which we have seen here. So NumPy gives you this for free and much faster. Indexing full row by full column slicing all built in. Here we also find out the shape of matrices which is using dot shape, and also if we find one particular value in a particular position, then we can initialize here. Also we can print the rows or columns what we needed here. So we have implemented here first row and first column. So in matrices, we also perform some operations. Example, reshape. If we have matrix shape 3 comma 4, then we can reshape it to 6 comma 2 and also reshape to minus 1 comma 2. Now let's see matrix multiplication. So here we implemented one formula which find out the matrix multiplication, and also we have compare with the inbuilt function of NumPy, which is this built-in function. Both gives us same results. So the matrices are used to organize and represent large amounts of data efficiently. So in machine learning, dataset, model parameters and transformations are all represented as matrices, allowing algorithms to perform fast and efficient computations. So that's it for all for this video. I'll provide the link of this Colab notebook in the description. Take a look at it. Let's end here. I'll see you in the next video.